Welcome to my talk on Care for Some Anions Anyone. This talk is basically about anyone. No, sorry, obviously it's about anions. So, well, anions are these exotic particles which I'll be talking about in this talk. And this will basically be following the work of Addy Stern and his article on anions and the quantum Hall effect. Okay, so this is the breakup of my talk. First, we'll be talking about anions, which in a very mathematical way, in a very abstract sense. I'll basically be telling you about the fractional statistics of anions and by what makes. Next, we'll be talking about how to actually get anions in physical situations. We'll be doing some thought experiments and we'll basically see anions as excitations in fractional quantum Hall states. Okay, then for that we'll use vortices and we'll actually see the fractional statistics. Come to that. Then this composite fermion theory is basically a theory for more exotic fractal quantum Hall states where we'll see anions come up again. Then we'll talk about a higher order class of exoticness of anions known as non-abelian anions. I'll be talking about all of this, then I'll summarize. Yeah, what I won't be talking about is this thing called real-Raszāi clustering approach, which is there at the end of my review. That has conformal field theory and it's basically related to the non-abelian ions, which I really don't want to get into because of the conformal field theory. I'll be talking about non-abelian ions only for the 5/2 fractional quantum Hall state. Okay, anyways, let's begin. So what are anions? So you would have seen this kind of an equation, this probability conservation equation, saying that if a two particle state is here, where there are two identical particles at R1 and R2, the probability after interchange should remain the same. Okay. And this kind of an equation leads to something like this, where you have a phase factor multiplied with the two particle wave function. Now we impose the condition that alpha is 0 or 1 only because upon interchange, the wave function shouldn't change, right? Now, and for 0, you get bosons, for 1, you get fermions. That's very obvious here. Now, there are two problems with this. First, we are being very restrictive by saying that the wave function should remain the same. After rotation or after interchange, okay, before this, let me tell you a rotation of a particle around another particle, the particle at the center, is actually equivalent to an interchange. Now imagine you take this particle, you're interchanging it, right? Like this. So it goes this way and this one comes down. Okay, now imagine in the frame of this particle, the other particle will actually be just going doing a 2 pi rotation upon interchange upon this interchange, right? Upon two interchanges actually. Yeah. So what I mean to say is two interchanges is actually very is equivalent to one rotation of a particle around another particle. Okay, we have that. That will be very important everywhere in this lecture for seeing the fractional statistics. Okay, now by putting alpha equal to 0 or 1 and saying that the wave function should remain the same, we are being very restrictive. Because why should it remain the same, right? It turns out that this is true only in 3 dimensions. In 2 dimensions, the situation changes a lot. Now for that, we actually study the path of the particle. Okay, so here you see these two particles, identical particles. This is just a diagrammatic representation. So here we are doing a clockwise exchange. Okay, now here what is happening is when you do such an exchange, you can always have another axis, that is the z-axis here, about which you can flip the diagram to make it a anti-clockwise rotation, right? That's very simple to see from here. But in 2 dimensions, a clockwise rotation will not be equal to an anti-clockwise rotation. And this is basically the crux of the problem. Now you can actually show that anions which live only in 2 dimensions follow statistics where alpha can take any value between 0 and 1. You can do that more mathematically using the path connectedness of SO3 and SO2 groups, but we'll not go into that. We are basically saying that these two are inequivalent, but in this case, clockwise and anti-clockwise exchange is the same. So in the 3D case, alpha can take only 0 and 1 because the wave function have to remain the same. Here they can differ because they are different. Okay, so these anions show fractal statistics. There are a more exotic class of anions, yeah, which actually don't just have a phase factor here. They have a unitary operator. So what that does is it makes it non-abelian. Now, abelian is basically related to associativity, basically commutativity actually, where you exchange one particle with another, and then this particle with another third particle that will be equivalent to, in the abelian case, the order won't matter, 1, 2, 2, 2, 2, 3. But in the non-abelian case, it may matter. Okay, because there will be two operators, u1 and u2, and they might not commute, basically. Okay, so this is basically all I want to say about the mathematical aspects of anions. Yeah, so this is basically the summary. There are two types, abelian, non-abelian. Now these are a very famous diagrams actually. They are world lines, time axis goes upwards. This shows anti-clockwise exchange, this shows clockwise exchange of anions. Yeah, and well, these are basically braiding diagrams which are used in topological quantum computing, but we won't go too much into that. Yeah, and this is very important. Rotating a particle around another is equivalent to 2 exchanges, so interchange is half rotation. Keep that in mind. Yeah, okay. Now we'll come to how to find anions in fractional quantum Hall states or fluids. And we'll see that these things known as quasi particles or holes, I call them quasi things, are actually the anions that we want. They show fractional statistics and they have fractional charges. Yeah, the fractional charges will lead to them having fractional statistics. Okay, so there are 4 ingredients, as you can see, around AB effect, which is basically the Berry phase, spectral flow, adiabatic theorem, similar things. Adiabatic theorem, actually, I'll come to a caveat here. There's a subtlety that we'll be talking about the adiabatic theorem and the use of Landau levels. Okay, and yeah, then I'll basically be talking about, I'll be starting here, the fractional quantum Hall state. We will take the fractional quantum Hall state as given initially. I will motivate why it's true after we have found our anions. Okay. Yeah, and we'll basically see quasi things. Let's just get started. Yeah. So from our course, we have seen already that this works. This kind of an equation where electric field is related to the current density. And this, let me remind you, is all in 2 dimensions. Okay, and yeah, and in the integer quantum Hall case, the nu, it can take integer values only, but I will for now enforce that it can take fractional quantum Hall, fractional states, sorry, and hence that this shows fractional quantum Hall effect. This is basically an equation for fractional quantum Hall effect if mu is fractional. Okay. Another thing I wanted to remind you about are the lowest Landau level wave functions. This is important because of the m values. Now you see the ground state, the lowest Landau level, is highly degenerate, and each degenerate state differs in the angular momentum. This will be very important. It'll be related to a subtlety in the adiabatic theorem. And yeah, this is an important equation. This also tells you that every electron is getting some angular momentum. Okay, keep these in mind, and let's move forward. So the Laughlin wave functions are basically wave functions for multiple electrons. Laughlin just gave it, and it turned out to be, well, it matched like 99% to the exact ground state. So he took a variational approach to get this wave function. Here, the m is the angular momentum, the relative angular momentum between two electrons. Okay, so this is, and the Zi, Zj are basically positions of the electrons, like in the Laughlin wave function. Okay, and let me remind you, Zi are basically complex number, x minus iy. Yeah. So for now, I'll be giving you the quasi-hole wave function. Quasi-holes are basically excitations of the ground state of the fractional quantum Hall fluid. Okay, I'm calling it a fluid because the electrons which show fractional quantum Hall effect the whole state behaves like a fluid. Okay, so this is like the ground state. This is an excited state where the neta refer to the position, eta refer to the position of the quasi-holes, the centers of the quasi-holes. Okay, as you can see at the center, whenever an electron approaches the center, the wave function goes to 0. That means the center of the quasi-hole is a charge depleted region. Yeah, this will be important in giving you an analogy with vortices. Okay, these are the things that show fractional charges and fractional statistics. Okay, let's see how. So for that, we'll be talking about a thought experiment. Here you can see there's a green color annular ring. This is a two-dimensional ring. There's a flux passing through it. This flux can be changed manually by us. And what we'll be doing is we'll be changing the flux, and like you have seen in the AB effect, your electrons move and they show spectral flow. Here, the important point is the subtlety that I was talking about is that the ground state of the lambda levels, sorry, the ground state of the fractional quantum Hall state is highly degenerate. You guys would have heard that the adiabatic theorem is only valid if you deal with non-degenerate states. The point here is there will be no level crossing here between the different states, primarily because we have taken an circular ring. Here, at every radius, you have a different angular momentum value, and these angular momentum values basically dictate which state you will be in, right? So there is absolutely no chance that you have any inconsistency or in which state you will be in while using the adiabatic theorem for showing spectral flow. Okay, so here in this experiment, we will be increasing the flux through the ring, annual ring, and what that does is it creates an azimuthal electric field in the theta cap direction. You can see that by the black line. Because of this and the fractional quantum Hall effect that I told you about, you get this equation, which is the radial current density. From this, you can calculate the radial current. The interesting part here is the radial current does not depend on the radius, on where you are on the ring. So basically, you start increasing the flux and you will start getting a charge accumulation on the interior of the positive charge accumulation on the interior of the ring. Yeah, and that charge is given by this. These are just very simple calculations that you can do. Now, what is interesting about this charge is the moment you reach phi naught, you get E nu. Now this nu is fractional, right? And because we are talking about Laughlin states, these nu are basically odd, and I mean they're 1 by m, where m is odd, and which basically describes fermions. Here, so this will be of the form E by m into phi by phi naught. Yeah. When it reaches phi naught, you have E by m only. So you get a fractional charge accumulated in the interior. Now, if you apply spectral flow, you'll see that, and adiabatic theorem simultaneously, actually, you'll see that this state that you get, the overall state, is basically an eigenstate of the final Hamiltonian, but also it's the ground state of the final Hamiltonian, but an eigenstate of the Hamiltonian that we started with. Every electron's angular momentum has been increased by 1. This can be seen from the Laughlin wave function. Here, you see by increase, what I mean by every electron's wave function has angular momentum has been increased by 1 is that when you multiply something like this, you get the powers of z here, which are the positions of the electrons, to have plus 1 angular, plus 1 exponent, right, from here. So yeah, so if the presence of a quasi-hole shows that the electrons that make this state have an increased angular momentum. Okay, so this thought experiment has showed that the quasi-hole, I call it quasi-hole because the charge is positive here, because this is a deficit of electrons. Electrons are moving outwards, hence it's quasi-hole. So this has a fractional charge in you. Yeah. There is another nice way of seeing the fractional charge directly from the quasi-hole wave function. Now you see here, you have m quasi-holes at the same position eta. Yeah. Now eta basically describes the deficit of electrons, and in this case, it is m etas describe a deficit of a single electron, as you can see. Right? Because if eta was just a parameter describing an electron, then this would give n plus 1 electrons in the Laughlin wave function. Yeah. So here, if m quasi-holes describe 1 electron, E by m or 1 by m quasi-holes, sorry, 1 by m electrons describe a quasi-hole. So that's just a simple way of seeing the fractional charge, or saying that a quasi-hole is 1 by mth of an electron. Okay, now I'll just tell you why fractional quantum Hall effect happens or works. I'll give you some motivation of getting this RH. It's very simple. So we saw that by moving uh, charges outside, by increasing the flux, some charge moves outside and you get a charge E nu here. So what if we move 1 electron? That we can do by increasing the flux to phi naught by nu. That will give this EMF and this radial current. And you can easily see that from here, that RH, that is the Hall resistivity or resistance, is indeed h by e square nu, where nu is fractional. Yeah. So this is a very simple derivation, kind of, just to motivate why fractional quantum Hall effect happens. Okay, so some important points. As I said, electrons, now when you create the quasi-hole, every electron gets every electron's angular momentum gets increased by 1. So we'll call that a vorticity. We'll think of electrons basically moving in circles around a charge deficit region, and it gets a vorticity of h cross. That is, every electron gets an angular momentum of h cross. Yeah. So yeah, just keep that in mind. We'll use it with for our analogy for vortices. Yeah. Now we'll go on to get the fraction statistics for quasicles. Before we start, before we get the fraction statistics, we'll talk about something known as vortices. Now, I want you to picture whirlpools, basically. They are basically the fluid with lot, with the center which is fluid depleted and a lot of water going in circles, right? So imagine a whirlpool and make that into something in 2 dimensions. You'll get something like this figure 5, yeah, where every point is basically a fluid, but the center is fluid depleted. So this is what I will call a vortex. This is basically what a vortex is, and I will enforce that every particle of this vortex has an angular momentum, has the same angular momentum with respect to the center. Okay, so now some facts about vortices and fluid dynamics, which I hope you just accept. You can go through other references to understand them more. So when a vortex moves, it experiences something known as the Magnus force. This Magnus force is given by 2 pi nl. You can see z cross, z cap cross, v cap, z cross. Z cap is basically coming out of the plane. Okay, and this is 2 for 2 dimensions. Now we will see. Now this, yeah, you see that this is very analogous to the Lorentz force. If you just make 2 pi nl equal to EB, you will get the Lorentz force here. So this is the primary analogy that I'm going to make to say that the the quasi holes basically act as vortices in fluids. There is obviously a more elaborate way of getting the analogy between vortices and quasi holes. That is basically you calculate the Berry phase, and you can actually see that every equation that you can get for a fractional quantum Hall state with a vortex with an excitation, you can get for almost, yeah, you can get for vortex in a fluid. The forces remain the same. Yeah. The thing is, what we'll do is we'll just use this directly. Yeah? We'll substitute this into the AB phase. Now what that gives is this. And once we make the L is the angular momentum of each fluid particle with respect to the center. If you make L equal to h cross, that is the vorticity equal to h cross, you will basically get that the AB phase is 2 pi times the number of fluid particles enclosed into it. As you can see, this is basically very analogous to the AB phase where it is actually phi by phi naught. So a flux quantum becomes analogous to a single fluid particle. Now a quasi-hole has electrons is a state with electrons which have a unit of vorticity, which is h cross, and it has a depleted region at the charge depleted region at the center. So it is analogous to the vortex. A quasi-hole is actually new fraction of a single particle, as we had seen before. E nu was the charge, right? So when we move a quasi-hole around a fluid particle, we just get 2 pi. But when we move a quasi-hole around another quasi-hole, we get 2 pi nu because its it's a fraction of a particle, right? This showed that this showed that the AB phase is basically 2 pi times number of particles enclosed, right? And this mu is basically the number of particles enclosed when a quasi-hole moves around another quasi-hole, because a quasi-hole is a fraction of a particle. So this basically shows you fraction statistics. How? That is because uh, a rotation is around of a quasi-hole around another quasi-hole is basically equivalent to 2 interchanges, as I had mentioned earlier. So one interchange will give pi mu, which is a fraction. And this is great because this is the phase that you get when you that is accumulated upon it. So you have seen here that quasi-holes show fraction charges and show fraction statistics, and it quasi-holes basically become your anions. So this is the first time we see anions in a physical model, and its anions are no more an abstract quantity. We can actually see them in experiments. Now we'll come to composite fermion theory. What I described earlier with the Laughlin wave functions is basically valid for nu equal to 1 by m type of states where m is usually odd. Here we'll be talking about more exotic kind of states, which is 2 by 5, 1 by 3. This is described by a different theory, okay, which we'll get into now. Here also quasi-holes will turn out to be anions, but how we get quasi-holes will be slightly different. And yeah, we'll be taking a field theoretic approach, and we'll kind of couple this with the analysis of wave functions to just make it easy to see. So let's start. The Hamiltonian of this theory will be given by this. This kind of makes sense because the psi is basically the electronic creation operator, and this term basically gives something like a psi dagger psi, which is a number of it. So this is a kinetic term multiplied to a number of it, which makes sense for a Hamiltonian. It gives the energy, and this is some interaction term, which basically takes into account all the Coulomb interaction. Okay, what we start with is something known as a Chern-Simons transformation, which what it does is it attaches three flux quanta to each electron. So you can think about uh, uh, flux passing through a two-dimensional surface with flux strings, and on the wall, an impenetrable wall, an electron is attached to p of these flux. So every one electron is related to p flux. Yeah, this basically happens because of this additional potential that we get. This happens because the small a changes the effective potential. This can actually also be seen simply from the Laughlin wave function. You can think of this as n minus 1 vortices or quasi-holes attached to a single electron. Yeah, because you can split this into n minus 1 exponents and 1 exponent. Yes, so it basically is also an equation of an electron attached to n minus 1 quasi-holes, where in this case the p will be equal to n minus 1. Now, without going into too many mathematical details, these electrons which have p flux quanta attached to them, which are the composite fermions, feel a mean magnetic field, V star. This is an effective magnetic field felt by every composite fermion. Now, because the effective magnetic field has changed, the filling fraction for each composite fermion will also change, as you can see from the number density equation. You can simply see that mu, that this is the filling fraction for fractional quantum Hall states, and mu star is for the composite fermion states. You see, if p is equal to 1 and mu star equal to 1, mu is half. So an integer quantum Hall state for composite fermions is actually showing fractional quantum Hall effect, right? So this is very interesting, and it will lead to us getting quasi-holes with fraction charges and fraction styles. So to get a quasi-hole in this theory, what we do is we annihilate a composite fermion from the ground state. Now this does something interesting. Instead of just removing one charge from the ground state, it affects all the other Landau levels for the composite fermion. So let's say a charge Q has been removed from the lowest Landau level. What this will do is it will change the effective flux felt by all the other levels, and it will actually increase it by PQ phi naught, right? PQ basically. Now here Q is basically a fraction of a charge. This is in the units of the electron charge. So this is basically a fraction. I'll be just saying that. We can always multiply it by E minus if you want to make it a charge. Anyways, so the charge of the lowest Landau level, the effective charge now, will be -1 plus PQ, because every charge, every flux quantum is related to a charge, right? Now, yeah. So because it has increased by PQ, here we have a charge also increased by PQ. And for all the other mu star -1 Landau levels, you'll just get an increase of PQ. The here -1 is coming from the initial annihilation of the composite form. Okay, so we have removed the effective charge of -Q, and we get this equation. From here, we can easily see that Q is something like 1 by P into mu star plus 1. So multiplying this by E minus, you'll get the charge of a quasi-hole, which is basically deficit of a composite formula. So yeah, so as you see, the charge is basically affected by all the Landau levels of the composite formula. And what we see is the phase is also very similar. Now say a quasi-hole goes around another quasi-hole in the same Landau level. Now I told you this is just a fraction, so it gives you a fraction of a particle. So the effective fraction of particles in the lowest Landau level is 1 minus pq. So the phase accumulated is just 2 pi times 1 minus pq from the analogy with vortices. And for a quasi-hole going around another quasi-hole in a different Landau level, and these Landau levels again are composite fermions Landau levels, right? So here it's 2 pi times minus pq, which is this. So you see, fractional statistics is very easily coming out from our definition of quasi-hole in this picture. Yes. Yeah, I think that's all there is to this. We have seen quasi-hole in composite fermion theory as fractional charge and is showing fractional statistics, right? And again, going around a quasi-hole is basically two interchanges. So half of this will be the phase accumulated upon a single interchange. Yes. Okay. So let's move on to non-abelian anions now, and then I'll finish there. Now, the non-abelian nature of anions comes because of non-abelian Berry phase. What we have done in class is basically abelian Berry phase, and here I'll talk about something known as non-abelian Berry phase. Non-abelian Berry phase comes because you have degeneracy present in the states, and you can there can be chances of going from one state to another. These transitions will be allowed. So the non-abelian Berry phase is actually a unitary operator. I will not be giving the definition of this, but sorry, the derivation of this. But yeah, you can believe me for now. This is the non-abelian Berry connection. As you can see, here you have two ground states, degenerate ground states, but which are different, labeled by A and B. So the Berry potential or the Berry connection is actually a matrix which gives you a unitary operator as the phase, which is multiplied with the state. This is known as a path ordering operator, which is very similar to time ordering operators which you've seen in the Wick's theorem. And you know it basically tells you which R came before which other R as you go through a path labeled by Ri's. Okay, so non-abelian anions are characterized through the Reid-Rezai clustering approach, but I won't be going to that. We'll just be studying the neutral to 5 by 2 states, and I'll basically be motivating the presence of non-abelian anions, and I'll show you how they show the non-abelian statistics. Now, in mu equal to 5 by 2 states, there are two filled nanolovels and one half-filled nanolevel. We'll be only interested in the half-filled nanolevel as that will show the interesting stuff. Now, because of the half-filled nanolevel, you'll see that the effective magnetic field felt is zero. There is the composite fermions do not feel any magnetic field. Yeah, we'll be working in the composite fermion picture only. Now, because the effective magnetic field felt by the composite fermion is zero, they can actually condense to form Cooper pairs, and this gives rise to something known as P-wave superconductors. There will be a few things that we'll have to accept here about superconductors. One is that the vortices in these superconductors are equivalent to half a flux quantum. So one electron charge is associated with two flux quantum. So one quasi-particle is actually quarter of electron's charge. So this basically happens because of Cooper pair formations. We will not be going to it. Here the charge of the quasi-particle or quasi-quark will actually not affect the statistics of the quasi-holo or the quasi-thing, as we'll see in the next slide. Now, as I said, mu equal to 5 by 2 states form P-wave superconductors, the Hamiltonian for which is given by something like this. Here, H naught is a single particle term, D is a pairing term. You don't have to worry much about it. What is interesting is something known as the Bogleubov-de Gennes equation. What this does is its solutions gives you excitations in the excited states in the superconducting ground state of the superconducting state. Yeah. Sorry. Yeah. So the BDG equation diagonalizes the Hamiltonian. Diagonalizes this Hamiltonian. Okay, and the zero energy solutions of this are something known as zero modes of the superconductors. They are basically excitations, and the unique property is that they are localized at certain points Ri, and they're given by this gamma function. This gamma can be labeled with I for that because there are multiple solutions, or J because yeah, J. So this gamma is localized at point Ri because this F decays rapidly for R much greater than Ri. Another thing is there's a phase factor here, which basically relates the position of every single vortex that you get. Now, an important because this Arjun. Now, the important point here is this gamma is a creation operator for the solutions, for the zero mode solutions. Okay, this is an operator, and this being an operator will give us the non-abelian statistics. Another point that I forgot to mention is that the zero energy solutions are highly degenerate, which should be obvious because you're getting multiple gammas from by solving the BDG equation with equal to zero. So here are some properties of the zero modes. I call them Majorana zero modes because of these two properties. Majorana are basically particles which are their own antiparticle. Okay, so these are basically the properties that you get from this equation. It's quite simple to see. Now, this you have. Now, we need to construct a fork space for this degenerate ground state. Now, how we do to actually analyze a ground state? Now, how we do that is by constructing these complex fermionic operators using these. So you have these properties for the complex fermionic operators. Now, the last property basically tells you that you can have a filled state or an unfilled state. And hence you can define something like a vacuum state, which on operation by the complex fermionic operator is a zero, and you can go on constructing states using the gamma dagger, which is basically a creation operator. Gamma is the annihilation. Now, because this capital gamma is made of two Majorana zero modes, the dimension of the Hilbert space spanned by the ground states that are created, these are all the ground states. Yeah, the dimension of the Hilbert space spanned by them will be 2 power n because there are two Majorana zero modes contributing to each number state. Now that we have seen that the ground state is highly degenerate, we want to know how to put between these ground states. So there's something known as braiding, which is used to evolve from one degenerate ground state one. Sorry, as the name suggests, braiding, we'll be moving things around other things again. So what we do is we move a vortex I, or this is the Majorana zero mode, around a vortex J, and we see that upon a rotation of 2 pi, the phase changes by e per I pi, which is -1. That can be seen directly from here. If you add 2 pi here, you'll get a -1 common outside. Yes? So we define a unitary operator for this encircling, and that can be shown to be given by this. This is because Uij only affects gamma I and gamma j and does not affect any other gamma ksa, which is not equal to I and j. So this you can work out. This is very easy. This is quite simple to work out, and you will get this. The unitary operator has to be this. The now you see this is the unitary operator that gives you encircling. So this basically gives you a phase when a vortex goes around another vortex. So for interchange, it'll be the square root of this operator, right? And remember, these are all operators. So upon interchange, you'll just get exponential of plus minus pi gamma I gamma j by 4. Now this unitary operator need not commute with any other unitary operator that you use braiding to go around, say, another vortex. right? So this basically tells you about the non-abelian nature because the unitary operators don't commute. You can read my review to find out why this unitary operator is showing non-abelian nature. It is basically because of entanglement, and yeah, and that these Majorana zero modes are actually correlated through this omega, as I showed you here. Rj and Ri, all of them are correlated. Right? A simple explanation will be that these creation operators are actually linear combination of the gamma j's. Now, this linear combination will basically give you a state which might be filled or might not be filled, a superposition of it being filled or not. And when a vortex moves around a filled state, it gives you a phase of -1. And when it moves around a state which is empty, it gives you does a phase factor of 1, which is basically no change. So while going from one, that basically makes you go from one ground state to another and gives you the and this entanglement gives you the correlation between the different states in the different vortex states. So in summary, we have understood uh, anions as a abstract mathematical concept. That's what we started with. Then we went through a thought experiment where we saw this anion in nature reveal itself through Poisson holes, and it's the same thing, no, similar thing we did for composite fermion theory. Then we saw non-abelian nature of anions in neutral 5/2 states, which are present in P-based superconductors. So I'll be ending my talk here. There are a lot of subtleties that I have not touched at all in this presentation, which can be read from my daily paper. I've mentioned almost everything there, except the part about superconductors. Uh, thank you. These are the references. Special thanks to Professor Dr. Gautam Sheikh for giving me the opportunity of doing this, and Navketan for his discussions and actually helping me find this paper. Thank you.